have two speakers today. The first speaker is Lisa Drummond, and Lisa is a Burke Fellow at Caltech, and after finishing her PhD at MIT this year. And previously, she was a master's student at the University of Melbourne, and her research interests are in compact objects and their gravitational wave emission. And so please take it away, and then I'll introduce the second speaker after that.
Thank you so much. Hi, everyone. Hopefully you can... okay, so thanks for that nice introduction. So my name's Lisa. I'm now at Caltech. I only just started 2 months ago, and up until then, I was a student at MIT across the road. So I'll tell you a little bit about myself and give you some background about what my research interests are. Maybe I'll stand over here. Okay. All right. So I'm a theoretical astrophysicist, broadly speaking. So I'm currently at Caltech, but I started my career in Australia at the University of Melbourne, where I studied neutron stars, specifically looking at the superfluid interiors and how these link to astrophysical observables like pulsar glitches. Then I moved to MIT about 6 years ago, and there I focused on modeling these systems called extreme mass ratio inspirals, which are sources for LISA. So I studied this sort of abstract concept called spin-curvature coupling, and I thought about how this would link to astrophysical observables like the gravitational waves we can see from black hole binaries. So basically I'm Lisa, and if you want to remember what kind of things I study, that's also Lisa, so it's pretty easy to remember. Okay, fantastic. So this talk is going to be focused on sort of this part of my research. So black hole binaries, and in particular focusing on like really unequal mass black hole binary systems. And these guys are called extreme mass ratio inspirals, sort of an obvious name. And I'm going to play a little movie for you. Hopefully it'll work. And it does have some sound, but we'll see if... Okay. So you're all familiar with probably the LIGO events that you see between more equal mass black hole binary systems. EMRIs are a little bit different. They consist of like a supermassive, much larger black hole, and then a much smaller body, which could be a stellar mass black hole, it could be a neutron star, or a white dwarf. And as you just saw in this little movie, the smaller guy makes many, many, many orbits, which are very complex and intricate. And as it orbits, it emits gravitational radiation and slowly inspirals into the supermassive black hole. By the end of the inspiral, the system is like in a very strong gravity regime, and it stays in that strong gravity regime for like many hundreds and thousands of cycles. Okay, so why do we care about systems like this? So I sort of already mentioned LISA, which, as many of you know, is the Laser Interferometer Space Antenna, which will be launched in, I think, around 2036 or so, hopefully. And it consists of this sort of triangular, equilateral triangle shape with these sort of space antenna and lasers in between, and it will be sort of following Earth with these like 2.5 million kilometer arms. And this gravitational wave detector will be able to detect systems like this. Okay, so that's great. They're astrophysical systems which we can hopefully detect with future gravitational wave detectors. But in addition to this, by studying these types of systems, we are getting insight into the relativistic two-body problem, which at the end of the day is super fundamental physics. Like, two-body problem is like one of the first problems that physicists have ever thought about. The relativistic version of the two-body problem is obviously much more complicated than sort of the Newtonian version, but it's still very fundamental, and it's kind of at the root of a lot of astrophysics. And this particular type of system, where one of the bodies is much smaller, because it's a much cleaner limit of the two-body problem, it provides a nice sort of lens to sort of analyze the more complex general two-body problem, if that makes sense. So it's just important fundamental physics that we need to understand and which can be applied to like a large number of different systems. Okay, so, right, we'll be able to see them with Lisa, but once, yeah, go for it.
What order of magnitude is this mass ratio?
Yeah, so honestly, like, so anything greater than like 10 to the 5 would probably call extreme mass, but actually it seems that a lot of these perturbation theory techniques are going to be applicable closer into like the more intermediate mass ratio regime, and that's something which I'll briefly mention at the end. So it's been demonstrated that you can quite straightforwardly map to something more like 10 to the 3, like an intermediate mass ratio system. So there could be a lot of relevance for these techniques to be applied to like, you know, LVK type systems even, potentially. Yeah.
Epsilon goes to 0, your signal goes to 0.
Yeah, well, I mean, okay, I mean, the number one issue is, you know, does epsilon going to 0, is there an astrophysical system such that that is true? I mean, potentially yes, like, you know, if you have like a particle of dust or something, but I mean that, yeah, the signal will go to 0, yeah, exactly. Yeah. So I think the sort of conventional range that people talk about is like 10 to the 4 to like, I don't know, 10 to the 9 kind of thing. Yeah. Okay. So, okay. So, right. So as I sort of mentioned earlier, having this large mass ratio means that this little guy is going to make hundreds of thousands up to millions of orbits, and this is a function of the mass ratio, in the Lisa band, potentially. And while it's making all of these orbits, it's going to be in like a strong field regime close to the supermassive black hole. So what this means is we can do things like really precisely measure the mass of the supermassive black hole and its spin, and we can do that to sort of this level of precision. That's what's predicted for EMRIs. And this means we can do things like test theories of gravity and test like the Kerr hypothesis for black holes. We can also do things like precisely measure the eccentricity of the orbit and things like that. And that tells us about the formation history and like sort of the environment around the supermassive black hole, like how did these things, you know, form, how did they come close to the center and stuff like this. So we sort of learn about black hole formation and the dynamics at our galactic center. We can also do things like infer the distance to the binary relatively precisely, and this allows us to do things like constrained cosmological parameters and the Hubble constant, standard sirens, this kind of thing.
Can I ask you a quick question?
Of course.
So I assume that you're solving the metric, you're solving
Yeah.
just for the central one? So the bigger
Yeah. So that's a super good question. Okay, so like at lowest order, yes, you just have your background metric. Like that's the dominant contribution is the metric of this guy. However, at higher orders, there will be a small perturbation due to the smaller mass black hole. So that'll be like a small metric perturbation, which you do add onto the background metric. But the background metric is like the 0th order solution, if that makes sense. Yeah. Okay. So just to give you a sense of kind of what an EMRI waveform looks like relative to the kind of LVK waveforms that you might be used to seeing, this is kind of, you know, sort of close to equal mass, stellar mass, you know, tens of solar mass black hole binary system, like GW17, 0817 kind of thing. And this is an example of an EMRI system. So this is actually, I'm trying to just demonstrate how many cycles you can get, and all of these cycles will be resolvable and will be like in band for Lisa. But this isn't even sort of as complex of a signal as we would expect. So this is like for a perfectly circular orbit of these two bodies around each other, whereas in fact we sort of generically expect that they'll have quite complicated orbital configurations, eccentricity, inclination. So this signal will be much more complicated. It will be really long and really complicated. That's what we expect for EMRIs. Okay, so this goes back to your question. So how do we actually model these guys? Well, very conveniently, the large black hole is going to dominate the space-time metric. And as we all know, like the metric of a rotating black hole is well understood. It's described by the Kerr metric, and that's going to be just our 0th order background space-time. Okay, so that's lovely. But you'll have these corrections due to the little guy perturbing the background spacetime. And I've written sort of first and second. The reason I stop at second is because we shouldn't need anything more than second order for sort of LISA data analysis. So that's sort of the kind of self-force program, so to speak, is computing these corrections up to second order. And hopefully once this effort is completed, we'll have complete EMRI waveforms which will be sufficient for LISA data analysis. That's kind of the broad idea. And just to, obviously this perturbation theory is being done in the mass ratio, which is a small parameter. Okay. Like, I would say so. I mean, there are divergences which this is kind of a complicated question. Okay, like at least I only consider a very small part of this perturbation expansion. So in terms of like overall convergence of the whole series, I wouldn't say that's something we know because we haven't actually computed all of the terms in this. There are open sort of fundamental conceptual mathematical challenges with computing in particular the second order part of this expansion. I would say that's maybe a slightly open question, but I would be confident that it is, but yeah.
To the equation of motion?
Typically to the equations of motion, but people have different approaches. People can do Lagrangian approaches, Hamiltonian approaches. Yeah, this is, like in my work, it's really just to the equations of motion, but yeah. Okay. So this is broadly the two kind of effects that we need to account for. And they're actually, they're in some ways interlinked, but it's sort of convenient to think about them separately, at least for this talk. So as I was sort of alluding to, there's this thing called gravitational self-force. I think you'll all be familiar with the concept of self-force and like electromagnetism and stuff like this. Basically, the effect of this small guy being in the metric will perturb space-time, and then that perturbation will act back on that small body itself. And then you have to account for the influence of this self-force. So this is what we call gravitational self-force. There's a second type of correction, which is spin-curvature coupling. So if you have any spin vector in any curved space-time, there will be a coupling between the curvature of the space-time and the spin vector. And this is not anything to do with the fact that this is curving the space-time around it. It can be like a body without a mass. So as long as it has spin, it will still have an effect, if that makes sense. And that will lead to like spin curvature force, and this is something which we also need to include. And this is going to be essentially the entire focus of this talk going forward. It's all going to be about what I call secondary spin, which is just the spin of the small black hole and how it influences the EMRI waveform. Okay. So here's my little cartoon. You have like a spinning top, which is really, it doesn't need to be a black hole. It can be any kind of spin vector, and you'll have this spin curvature force you need to account for. Okay. And then here's sort of our black hole background space-time, and these two things are coupled. Okay, so this maybe looks a little bit complicated, but all I want to show you here is that we have a gravitational wave signal, it has a phase, and we have a bunch of terms that we need to compute. Okay, so this is the leading order contribution, which is quite well characterized in sort of the current state of the field, so that's great. Now there's all these things which people call post-1 adiabatic effects, and this is sort of where the theoretical front is at the moment. So there's several different terms here. These blue ones are self-force terms, and the red ones are the secondary spin, or like spin curvature type terms. This one here is the second order term that I was talking about that people struggle with and is currently not computed fully. But really all I'm going to focus on is this red box, which are the secondary spin terms. And I'll just make a note that because this is perturbation theory, these can all be computed separately and just added together. Because any cross terms will be higher order in the expansion, so everyone just sort of tackles these things one at a time, and the hope is to combine them all together into one big expansion, and these will all contribute to the gravitational wave phase, and we'll be able to characterize EMRIs super precisely. Okay, so I have this flow chart down the bottom. Once again, I'm not going to go into any of the detailed math behind the individual boxes here. I basically just want to point out that the calculation of these things is not like one simple integral or something. It requires a lot of analysis and a lot of calculations of different components that then need to be combined together. Some of it's numerical, some of it's analytic, and there are all kinds of different pieces. Yeah?
The blue ones up there.
Yeah.
Does cons mean conservative and dis?
Exactly.
I'm just curious what dissipative forces.
The dissipative forces are due to the gravitational radiation. Right, so the leading order contribution this is actually the first order gravitational self force, orbit averaged, and only the dissipative piece. That's the leading order contribution. And then this is like the conservative piece of the first order gravitational wave self force, and this is the dissipative orbit averaged second order self force. Yeah, so basically people break it down into as really small pieces and they calculate them as well as they can and put them all together.
Sorry for the interruption.
Yeah, of course. No, please.
Context.
Yeah.
So you're doing this for relativity.
Yes,
Everybody heard it.
exactly.
Solved for same mass bodies? No, right?
No.
You would just
Numerical relativity. That's a super. This is semi-analytic. You can't do it fully analytically. We try and do it as close to analytic as possible so we can compute these things as quickly as possible. They're still going to be faster than numerical relativity because at the end of the day, you end up with like a system of ODEs as opposed to like complicated PDEs like in numerical relativity. It's always going to be much faster even if we're solving it numerically. But the point is, I should have mentioned this earlier, you can't really solve these systems with numerical relativity. There's just too many cycles. It's just sort of computationally intensive. So you can sort of push out to, I don't know, like maybe mass ratio 100 or something. In some NR simulations, there'd only be a handful of those anyway. Not really any further than that. Yeah, okay. So you really need this. You need the perturbation theory. There's no other way to do it. Okay. All right, so I'm going to talk about this kind of flow chart. Don't worry, it won't be too mathematical. I'm just sort of trying to give you the physical motivation behind all the different pieces, okay? So this top part is the conservative stuff. So it's the corrections to the frequencies due to the presence of the spin curvature force. I'm sure you're all familiar with the geodesic equation for a non-spinning body. When you add spin, it's essentially just a modification to the geodesic equation. You just get this little extra force, which is the coupling between the Riemann tensor and the spin tensor of the small body. And this is the spin curvature force. And you just solve the system of equations. And sort of physically what it does is it causes the spin vector of the small body to precess. And it also sort of perturbs the motion of this little guy away from the geodesic. So this was sort of the first part of my PhD work, is to compute sort of semi-analytically the solutions to this system of equations, and in particular compute the corrections to the orbital frequencies. And we did this for completely generic orbital geometry, so not making any assumptions about circular orbits or like confined to the equatorial plane. And the reason why this is important is because for LISA, we believe that the way these EMRIs are created, they're likely to have a significant amount of eccentricity. They'll potentially be inclined. You need to have a fully generic orbital configuration. So really the first time these equations were solved in such a way for described in terms of their generic orbital geometry are in these two papers here. Okay. And I just wanted to give you a little example. Okay, so this is the setup. You have a big black hole, little black hole, and orbital angular momentum vector. In this case, the orbital angular momentum and the spin of the small black hole are aligned. They don't have to be generically. They can be misaligned, of course. So this is just to show that basically the trajectory of the spinning body deviates from a geodesic. And I've actually aligned these so that their frequencies are the same. There'll also be a dephasing due to the different frequencies as well. But the shape of their trajectories will change as well. So this is sort of their radial motion and polar motion. Okay. And you can see that there's sort of more complicated harmonics And yeah, it's just a little bit more complicated. Okay, so that brings me to this next piece of the flow chart, and these are the dissipative components. So that means the gravitational radiation. So as this thing orbits, there's going to be like a non-axisymmetry, of course, and so it's going to radiate gravitational waves. And there's going to be basically a correction to the stress energy tensor due to the presence of this guy, and that will change the gravitational wave fluxes that we observe. Okay, so just a little bit more rigorously, for like just a point mass, like kind of a geodesic orbit, you would have a stress energy tensor that looks like this. And then for our spinning body, you'll have this extra dipole correction, which is obviously going to be a function of the spin vector of the small body. And in order to find the gravitational radiation, you solve something called the Tarkovsky equation, which maybe you're familiar with, where this source term here is a function of these stress energy tensors. Okay, so that's sort of an overview of the calculation. It's okay. That's an overview of the calculation, and sort of our ultimate goal is to combine all of these pieces together. So we compute the kinematics for sort of a single orbit. We compute the gravitational radiation of that orbit, of the small body, and then we sort of compute how that is going to backreact and cause the small body to inspiral. And we piece all of these orbits together, and we have a gravitational wave-driven inspiral. That's kind of the idea. So what I want to do now is just fill out this parameter space and show you what we've currently done in this field and what remains to be done. Okay, so as one does in theoretical physics, we start from like the simplest possible case, and then we get more and more complicated. So we start with circular, aligned spins, confined to the equatorial plane, and then we sort of increase the complexity out to generic orbital configurations. So 5 years ago, at the start of my PhD, this is where the state of the field was. Oops. We just had this corner filled in. Obviously, we want to push it down to here. We want to have the full gravitational wave-driven inspiral, and we want to have fully generic orbital configurations. All right, so from like 2019 to today, these are all the papers that came out. So some of my work was computing the sort of orbital kinematics for a spinning body for generic configurations, and then a number of people computed for sort of more constrained orbital configurations, the gravitational radiation. And as you can see, we're sort of pushing closer and closer to this corner, but we're still actually not fully there. So now I'm gonna tell you in a little bit more detail about what's going on for this generic case. Okay, so this is some of the work that I've done in my PhD, computing this part, and also computing the gravitational wave fluxes. So one might imagine that you could put these two things together, and you'll have the full inspiral, okay? However, there is a remaining, go ahead. Oh, sorry, okay. Okay, so you might imagine that all that remains to do is just combine these two things together. Unfortunately, there is one technical challenge, which is we don't know how the Carter-like constant evolves for a spinning body. So if you're familiar with Kerr geodesics, they have a Carter constant which is conserved. Spinning bodies are the same, but we don't know how that evolves as they radiate gravitational waves. So that's sort of the remaining challenge, to piece everything together. Okay, so what I did is just to do a first kind of pass to study the dephasing due to spinning body effects, is we just wanted to see how the corrections to the frequencies are going to influence the waveform and potentially affect like parameter estimation and things like this. So we didn't include the corrections to the fluxes, but we include the corrections to the orbital frequencies, and we produce this waveform here. Okay, so you can see, as one would expect, if you have these two things initially in phase, by the end of this waveform, they're going to be out of phase. So the blue is the spinning, and the yellow is the non-spinning. Okay. And by looking at the size of this dephasing, we can see how detectable this is going to be with LISA, and it will be detectable. Okay, and I just make one comment that in order to compute these waveforms, one thing we had to do is speed up the computation of the trajectory. And in order to do this, we kind of have to average over all of these small oscillations. So if you want to compute this numerically, you don't want to be integrating over like hundreds of thousands of oscillations, because these will be sort of higher order in the expansion, these little oscillations. So we just use a NIT, or a near identity transformation, and solve for only the evolution of kind of the averaged quantity here. Okay. And this allowed us to sort of speed up the calculation by 2 to 5 orders of magnitude. And we use this as input for generating the waveforms. Okay, so I'm at the end now. Okay, so the sort of 3 takeaways that I wanted to end with are that this field has advanced enormously in the past 5 years, which is during my PhD. And what we've done is we've been able to model these spinning secondary effects for completely generic orbital configurations and accelerate the computation of the trajectories. And this is really important for Lisa data analysis. Okay, that's it. Thank you so much.
We interrupted her a lot. I'm sorry that we interrupted you a lot, but that covered kind of the question.
Yeah,
so let's do one quick question. And
Would any of this make much difference if the secondary was a star and not a black hole
Yes, yes. So
of equal mass?
say it again.
The star has the same mass as the black hole.
Yes, yes. So it's still gonna, yes. So the only difference with a star, well, I guess there are 2 differences. First of all, it's going to tidally disrupt earlier. So it's not going to get as far into the strong field.
If it's a big enough black hole, it won't.
Yes, if it's a big enough black hole, it won't. The second effect is you'd have to actually think about higher order corrections in the multiple expansion. So you'd have to think about like quadrupole, not just dipole corrections.
Because of distortion.
Because the star, yeah, exactly. But those are the only things you have to think about.
If we were a white dwarf, maybe.
Yeah, if it's a white dwarf, that would be, yeah, absolutely. So people definitely think about this with white dwarfs. It doesn't have to be a black hole at all. Neutron star, white dwarf, yeah. Yep.
And are you around right after this?
Yes, absolutely.
Yes, but I think we have to move on,
yes,
and anybody can ask right after this. Thank you so much.
Thank you so much. Yes.
Okay, let's see.
Okay.
Do you want to try to connect while I introduce you? So the second speaker is Congyue Deng. Congyue is a last year PhD student in Stanford, studying computer science, and she is interested in, a lot of her work is in applying geometrical machine learning to the physical sciences. So she's been visiting us in AstroAI and also visiting the group in MIT in this area, so she comes often. And yeah, so she's going to talk today about geometrical machine learning. Did you get any?
Let's see how it works.
Okay, there we go. It looks like it's working. Oops. Okay, perfect.
I'm not sure how it works. Oops. Oh, I see. Oh. Do you know how to switch sides?
Yeah, you have to.
Oh, I see. Okay, the laptop's safe now. Probably I'm just gonna use my laptop.
Does it work, Mike?
It doesn't really work for my laptop. Maybe I'm just gonna do this.
Okay. And what about the mic? I don't think
I think the mic is kind of working.
Okay.
Okay, cool. So hi everyone, I'm a 5th year PhD student from Stanford. People ask me what I work on. I usually joke that I work on coming to Boston and sneaking to the meetings at MIT and Harvard. So, but generally I work on building neural networks for machine learning problems with the understanding and enforcement of geometry relations. And currently I'm also collaborating with Cecilia and also some other people at MIT Computer Science about using geometric neural networks to learn physical properties. So a little bit introduction, why do we need geometry in neural networks? So in the past, geometry had been a very important language for describing physical laws. For example, there's a well-known other theorem which says every continuous symmetry in your Lagrangian is describing the law of conservation in your physical system. And also, like as just described in the previous talk, like people use like Riemannian geometry, the curvatures, to describe general relativity. And this is a meme which I really like, which is saying that the bat has more gravity when you don't want to get up than everything else in the world. So how do we have these things in neural networks? Or without these things in neural networks, can we still use neural network to process the experimental data of physical things? And I think usually the answer is not really. So in the past decades, people have been developing neural networks in a very seemingly intelligent way. For example, they can tell you whether an image is a cat or a dog. So it's like when they see something, they can understand your visual signal or visual data. However, building geometry into your neural network is like equipping the neural network with some measuring equipment, which is instead of directly seeing what you see, it's also trying to understand and analyze what you're seeing. And moreover, in recent years, so in computer science areas, people have been actively developing these generated models where they can generate like very cool videos or very cool images. So it's more like most of these neural networks for like visual data generation, it's like a very nice artist in the world. But think about that, if you really have a science or engineering problem that you want the neural network to solve, you don't want to invite the best artists in the world to draw figures about those science problems, but instead, you want a real scientist or engineer who understand these geometric relations to draw these things for you, so that you can really have these relations in your generation results. And a little bit more about how neural networks are really tackling this problem. For example, here is a standard training setup for neural networks. So you have a collection of data. For example, all these data follow a certain distribution. You train a neural network on this. You have annotations about what these data are about, and you train this neural network. And then if you have a new data, your network can tell, okay, I've seen something like this before, so I can recognize this new thing following the data distribution. However, what are the problems about most of the neural networks is that if you have slight distribution shift at your inference time, so for example, you have a new set of experimental data, for example, now it's a similar thing following your training data. However, you have a rotation applied to that. So you have a 3D rotation applied to the new data, and then most of the network will directly fail. Even as a human, you can easily recognize these things are the same under a rotation. Actually, it's a SO3 group action, but for neural networks, it's a super hard problem. So how do people tackle this? So in the past years, I've been focusing on enforcing geometric relations into neural networks to allow the neural network to really understand these geometric transformations. So specifically, there's an area called equivariant learning in neural networks, which is saying that if you have a group action, which is a linear transformation applied to the input data of your network, can you enforce that your network can have similar or consistent understandings under those transformations? So for example, if your data observation is transformed by a 3D or 2D or whatever linear transformation, can you still have exactly the same output in your neural network? So this is a problem called equivariance in neural network learning. And if we really look into the mechanism of a neural network, we can try to see how these problems come from and how we can potentially tackle this problem. So why can neural networks do all those fancy things? So basically, a neural network is a highly nonlinear function, which is a black box because they have so many parameters. And also, these parameters can be optimized through your data. So here the blue circles are the input data you have, and the light blue circles are the output of your neural network. And all the values in green in the middle, they're called the hidden activations of a neural network. So all the circles here are values, and all the arrows here are functions which have optimizable parameters. And specifically for all the values in the middle, for a whole stack of those values, we call it a latent feature of the neural network. And specifically for a set of features for all your data that you use to train your network, we say it forms the latent space of the neural network. And in the past, people have been spending a lot of time studying the latent space of a neural network, whether they have some manifold structures, whether they follow the same manifold structures of your data, or whether they can follow some assumptions. And people do have discovered something. For example, this is an example for applying neural network to natural languages of human, and you can see that, for example, for the verb tenses or for the country capital, you can clearly see some relations of the primal data and their latent spaces in your neural network. However, can we find or can we enforce similar things specifically for geometric relations, such as some diffeomorphisms or some group actions into the latent space of the neural network? So in such a case where neural network can really understand these things. So one of my past work have been focusing on that is that, so this is a standard latent space of a neural network where here the yellow blocks are actually the green circles in the previous figure. And now it's like, instead of using those scalar values to represent these features, I've been extending each of the value to a 3D vector. So for such a 3D vector, a very direct thing you can do is that, so now that you can apply group action from this side. So you can really apply linear transformations or any other geometric transformations that can be applied to a 3D vector to this whole stack of latent feature of the neural network. And also, if you have more complex group actions or more complex geometric transformations, you can further extend these neuron representations so that the neural network can be used to express these geometric transformations. And so we've been talking about the representation space of the neural networks, and now we can talk a little bit more about the operations or the black box parameters of the neural network. So the arrows between two layers of the features are a layer of operations. So specifically for one layer of linear function, for one layer of neural network function, you really have two components. One is a linear operator, where you're applying a linear transformation to a learnable linear transformation to your features. And then followed by that is usually a nonlinear activation, where usually people use this ReLU function, which is piecewise linear, so that you have very controllable gradients. And following the geometric representation of the neural network features, what we can do here is we modify all the operators in the neural network so that they follow all these input geometric transformations. So for the linear layer, it's a direct extension to standard neural networks, where instead of taking linear combinations of the scalar values representing the features, we take linear combination of the vector values representing the features, and this is commutated with a group action. And for the nonlinearity, we further modify the standard ReLU, which is defined on standard Euclidean coordinates, to a 3D rotational version, which is dependent on the input data. So this is like for standard ReLU function in most of the neural networks, they're like if your feature value at this layer is above 0, you keep it unchanged, which is as shown as a function here. And if it's negative, which is below 0, you clip that to 0. So here we extend it to a 3D case, which is dependent on the input data, where you learn the direction k from the input data. For anything that is above the plane defined by k, which is perpendicular to k, you keep the feature unchanged. And for everything below the plane, you clip it to the plane. So going back to our neural network, where you have all these mechanisms and the functions, how do we make the neural network geometric? This is very easy, where you change the latent representations to the geometric version, and you change the linear function into the modified linear version, and you also change the nonlinearities to that version. And in such a case, the neural network can have such equivariant properties where you can express the group actions or transformations in the latent spaces. And upon that, we also built a little bit more variations of the different components of the neural networks, where together form a neural network toolkit that you can replace the standard operators in a neural network. And with that, let's go back to the original problem where, for example, you train on the data on the left, which is this one is a surface fitting problem, where you have some discrete data points observed as a point cloud in the 3D space, and you want to fit this continuous surface to those data points. And so on the top, the pink one is a standard neural network, where you can see that if your data is in distribution, which you have seen this pose before, you can fit the surface very well. But if you apply a rotation to the data, the fitting is totally ruined. So for those neural networks, they really don't understand these kind of transformations. But with all the modifications at the bottom, which is a yellow one, if you rotate the data, the fitting is always consistent to your original data distribution. And here's a better visualization of that, where the yellow points are the input to the network, which are the discrete samples you can observe. and the blue surface is the one that you're fitting with the network. And this one is like, this one is not like just rotating with a visualizer, but it's really like inferring at each of the frame. So you can see it's very consistent predictions. And it can also be applied to finding that surface in a larger scene of data points, in a larger scene of the points in 3D, where we've been doing this EM algorithm with the neural network in the, I think in the E step. And here are some of the results where you have like all these points observed in 3D, and you can locate these objects and as well as finding the poses of them using the geometric neural network. And going a little bit further, so beforehand, I've been talking about one of the most simplest geometric transformation in 3D space, which is a linear transformation. So how about if we have a more complex system? So one extension to this linear transformation is a multi-body system, where like you also have this two-body problem in astronomy, which a lot of people care about. So one problem in machine learning we care about is that, for example, if you have a whole, observation of the whole system, which is shown at the top, and you have no knowledge about that, can you segment the system into parts where you know, like, okay, this one like all the data points here, their motion are the same motion, and all the data points there, their motion are the same. So can we further extend the equivariant property to this multi-body problem? And the answer is yes. So, but before tackling this problem, there's actually something hard in the formulation itself. It's kind of a chicken or the egg problem, where like if you, so basically we want to build equivariance to this system to find the parts of the, to find the part of each of the system. But on the other hand, the group action itself is defined by how we define the parts. Because like if you know the parts, you can say, okay, all these points in this part, they move together. But if you don't know the parts, if you have a wrong estimation of parts, your network can probably make things even worse. So however, to tackle this problem, we've been formulating this into a fixed point problem. So specifically, we're saying the whole observation of the system is a condition to this fixed point problem. And we can do iterative inference on the segmentation of the system, where you start with a random initialization of the guesses of the parts, and you gradually converge to a final prediction, which is consistent to your training data. And specifically under certain assumptions, like the Lipschitz assumption of the network function, the convergence and the equivariant property can be proved in such a system. So here's a clear example where on the very left is the training data we have, where you can see that the parts are under certain under certain states, which is a rest state, where the angle between the two parts are 0. And on the right are some new training, are the new test data, which are totally different from the training systems. But you can still see, like, starting with some random initializations, the network prediction can gradually converge to a state which is consistent to your training data.
Quick question.
Yeah.
The training state, so let's look at your box at the bottom left.
Yeah.
Do you have any training information that it doesn't open the other direction?
Sorry, which one? This one
The
or?
far left. Okay.
This one?
That's the training set, right?
Yeah, that's the training one.
Does it have any, is there any information in there that instead of opening down, it opens up?
Oh, that's a very good question. So this one, we're actually assuming free motions to each part of this box. So actually, like, you can also tear it apart into two separate parts. So because like for modeling the system with a group action, like you need to assume like free motions, and this additional constraint is a little bit hard to model simply using the group actions. And we've been testing some methods to enforce that numerically, but not like really analytically.
Okay, so I guess I don't totally follow. How do you get that it always opens up in the bottom?
Oh, so your observation or input to your network inference is always a point. So all the points, like all the dot plots here, are the inputs to the network, and the network is trying to infer the colors in this. So specifically, like the probability distribution, like this point belongs to this part and this point belongs to this part. So this is our training data, which contains both the observation of the points and the labels or the probabilities on top of that. And so here are the inference where you only tell the network what the points are, and you don't know the probability on that. So it's like, So what the network is doing is starting with a random probability, random initialization, and gradually do inference to converge to the final prediction.
So tech, it could go either way.
Sorry?
You could open it either way, and the program would probably do that, right?
Oh yeah, yeah.
Okay.
Yeah, that's an interesting question. And here are more examples of the inference where on the top are the training states, and on the bottom are the inference under different motions. And you can see the overall inference is quite consistent to the training ones, even under the state changes. And here are more examples. We've been trying to test our network with some synthetic data, which look very fake, where you put everything axis in line and all the data are pretty clean. And we try to apply our network to inference, which are actually scanned from the actual 3D scenes. And you can see there are the scan noises, and also like the poses of these objects in the point observations are very different from the previous one, but still it can gradually converge to the state that are consistent to the training data. Okay, going a little more, so we've been talking about linear transformations, piecewise linear transformations. What else can we do by enforcing geometry in neural networks? So let's go back a little bit about an overview about what neural networks can do nowadays. So in the past, like ever since the beginning of the development of deep learning, people have been trying to tackle this problem of like whether this image is in cat or dog. So it's a very high level understanding of the visual data. And afterwards, people have been trying to apply neural network to more fine-grained problems. For example, can you locate the cat in the image? So where it is, can you draw a box around it? And later, people have been trying to make it like more and more fine-grained. For example, can you analyze the image by regions? And finally, can you even understand every pixel in your data? So for example, if you have these two images, can you correlate all the pixels, or as many pixels as possible, like what is happening between these two images? And what we've been trying to do is that we want to tackle the most fine-grained problem, and moreover, we want to incorporate geometric understandings into this problem. If we look at this problem, so going back to the problem itself, it's actually asking you, okay, you have these two images on the left. What if something happened from the first one to the second one, and you want your neural network to tell you what is happening from the first one to the second one? And then most of the neural network can give you such an estimation, for example, of correspondences or the transportation of the points. However, if you ask a human to process this data for you and to describe and to summarize what's happening, a human actually will not directly give you such a low-level thing. What a human usually will answer you is the object deformed. So for human, when they're trying to do this data analysis, they have some more high-level understanding of what's happening. And can we also incorporate such things into a neural network? So using something high-level to guide the process, to guide the data process of neural networks. So specifically to address this problem, we've been doing some spectral decomposition in the latent feature of the neural networks. Recall that the latent feature is a green things in the hidden layer of the neural network. So because like they're kind of forming a space, and with all these data, we can do spectral decomposition with all the features together. So specifically, this is a spectral decomposition example, which is not neural network yet, but with a simple data case with a Laplacian Beltrami operator, where you have this Laplacian operator, which is very similar to the Fourier transform, but here is a manifold case where you have this Laplacian operator. You can take all the eigenvalues and eigenfunctions of this operator, and here are the visualizations of the eigenfunctions. And all these eigenfunctions together, they can form a function space of the data or of the manifold. And after having the spectral decomposition using the Laplacian operator, what you can do is that recall that we want to estimate the correspondences or the point mapping between two images. So now it's like with the spectral decomposition, without representing this mapping as pointwise mapping, which is like mapping this point to that point, drawing a line here to there, you can map them on all the spectral sequences using an overall functional map. And now, like one very good property here is that if you're mapping the diffeomorphism with the spectral analysis, it is actually can be represented as a linear map. So we've been trying this thing, the spectral decomposition, all the features of neural networks instead of the original signal you see as the input. So these are the latent features of a neural network, which is very high dimensional in most of the cases, but here we're visualizing the features using PCA. So we're only seeing the first three principal components here. And on the right are the spectral decomposition of these network features, where you can see that with the eigenvalues of lower frequency, here are the lower frequency ones, where are the eigenvalues of the first couple of indices, and here are the higher frequency ones. And with this spectral decomposition, we can compute the linear mass between the spectral sequences of two images. So here are the source and target images. We want to analyze what is happening between, or what is the correlation between these two images. So we compute the spectral decomposition before, and here, so here every column corresponds to one of the function bases of the source image, and every row corresponds to one of the spectral, one of the eigenfunction of the target image. And here the diagonal ones, here we're testing with different features, and the diagonal ones are usually a better matching because they're matching things of similar frequencies. And here are some visualizations. So with a functional map, how can you go back to a pointwise map? Is that you can view each point in the image as a direct delta function, and you can still map this direct delta function in the function space to a function in the second image. And by doing that, you can convert the functional map in the, on the spectral sequences to the pointwise map on the images. And here, this rainbow color is the coordinate system visualized on the source image. And here we visualize how the coordinates are mapped to the target image. And this is a baseline method with a standard neural network where you directly use the features of a pre-trained, which is a very nice neural network trained by Meta. And now this is like their method combined with our method, and you can see that by applying that spectral analysis, you can have smoother maps and you can have more consistent geometric interpretations. Specifically, here's an example I really like. So you have a red region at the neck of this bird, and you want to map the coordinates from the first bird to the second bird, and you can see that if you directly apply a standard neural network, it's very hard to find the neck here because the region is almost error zero. So you almost have no pixels for that region, leaving for that red thing. But if you use this geometric consistency, the network can somehow understand the overall mapping of the entire shape. So it's kind of understanding, okay, the red region should be something that is between the head and the body. So by doing that, you can now find the red region that corresponds to the first image. And another very important application of this functional map is that you can use it to transfer a heat map, because a lot of data annotations, they're not annotated as per point per point annotation, but instead you probably want to annotate some heat maps, like this region in the visual data represents something. So for a heat map, it's a probability distribution on your image. If you directly transfer it as a point map, it's very hard. For example, if this pixel has 0.5 probability, how can you transfer that? But the heat map itself is a function, so it also lives in the function space. So you can directly decompose the function, which is the heat map, with the basis. So you compute the basis expansion of that function, and you can directly map that function with a functional map. So by doing this, we can directly transfer a region or a probability distribution from the first one to the second one. Okay, I think here are all the works that I want to cover. And at the very end, I just want to show something that motivates my research, where people have been saying the reality of the universe is geometrical. So probably if we want to apply a neural network to understand the universe, it's better to make it also geometrical. And also, people are saying that understanding the representation of what nature is really like is important. So probably we also want to understand what the representations, which are the great things in a neural network, how they are really like. And I think that's it.
Thank you so much, Congyue. Are there any questions?
Yes.
I have maybe a silly question. So when you were showing the chairs rotating and how you could match the fit to the surface, is that a perfect match with the rotation, or is there some loss when you do the fit after the rotation, if that makes sense?
Yeah, that's a very nice question. So it is a perfect match because we're enforcing that transformation already into the operators of the network. Yeah.
Another question.
Well, thanks for the talk. So related to the SO3 invariant stuff, what I've seen in a very different context, but conceptually very similar, and what I wonder is what I'm about to describe the same as what you're doing, which is taking, let's say, a large set of three-dimensional coordinates, finding some sort of principal axis system, something like that, some moving frame, and then just re-representing Cartesian positions in that moving frame, which is an inherently SO3 invariant, and then just doing everything you would do in any normal network after that. Is that equivalent to what you're doing, or are there some important differences?
That's a super nice question. So I guess like one very naive way of finding the three coordinates is the PCA methods. But usually in a lot of cases, like using PCA is a little bit more like numerically unstable. And also like I think it also depends on like for finding the principal axis, like how do you define the principal axis? Like, do you want it to be like more semantically meaningful, following the distribution of the data, or do you want it like more like, like numerical for this specific data point? So I think using a network to predict that is more like you're predicting some consistent coordinates of all the data. And I guess another difference is that for certain type of data, probably it's hard for you to define what is actually the principal axis. So at least like for some of the cases, like the chairs or the tables here, I think most people will say like these are the principal axis, like following the coordinate like a cube. But probably like for some more complex like geometric shapes or representations, it's also hard for you to define a consistent axis system across a whole bunch of data. So I think that's why like machine learning methods on that could be useful.
Mm-hmm. Thanks.
Okay, any other questions, comments? If not, let's thank both speakers again.